Okay, so once again you are most welcome. Okay, my name is Mtanda Samir. Please, it has been a long time, I know, ever since we last posted, but of course, just to maybe remind you, I'm also a teacher by profession, and I always get some calls which get me busy. Okay, like in those days, which are where I have been away, and the senior force were meant to report back. We were meant to even have a facilitation with them online here, but I wasn't able because I also have some stuffs okay I engage in actually more especially facilitations. Yeah? Okay, so that is it. That's the reason why I've been a bit away. But anyway, we are getting back in style. Sorry, I know most of the senior folks have reported back for their final exams, but okay, no worries. Apart from the day scholars, but of course I was told the schools with the smart TVs, they are able to have this watched. Yeah, anyway, that's a good way to go. But for those who don't have them, and of course in schools they don't allow phones, I know they won't have access on this. A simple reminder: my name is Mtanda Samir. Okay, please, my contact there is the very one I use on WhatsApp. But please, maybe I want to send out a sincere apology to you people. Please, you okay? The issue is I don't really I don't refuse. It's okay. You can send your questions, but just know I'm also always occupied, just like you are. So someone comes, sends over 30 items, and someone is telling you, "I want them in 30 minutes." Anyway, so that is it. Anyway, but I humbly submit my apology to everyone whom I was not able to reach out. Please just forgive me in simple terms because I'm also a busy human being. All right. Of online work here, I also get other stuff which made me busy in the long run. Yeah. So I've kindly apologized to whoever I was not able to respond to. And please, just to let you know, I receive over 30 texts from different people, new ones every day. So I may not have been able to respond to yours just because I may not really be able to reply each and every person. But then I'm very grateful for whoever comes forward and comments, appreciating the great work we're doing here, and those who still come in the inbox. Yeah. Anyway, any form of appreciation, we really appreciate that. All right. Without wasting time, I think let's get there. Okay, we again remind you to subscribe to the channel, please. You realize that still, like I've been telling you, somewhere we are going to have this channel limited to only our subscribers. And of course, guess what? For whoever will have not subscribed, you will be forced to subscribe with some payments. Anyway, I may not want to go into that. So better subscribe such that you don't fall a victim. Alright, then please, as teacher Mtanda, this phone here of mine, this phone number of mine, sorry. Alright, so without wasting time, let's proceed. We simply remind you to subscribe such that you don't fall a victim. Alright, so with that, let's get on to our item. Alright, our item 6 of Jjeb 2025. Alright, please, for those who have not watched the other items, we have the items right here from item 1 up to where we are right now. And sooner or later, you keep checking on the channel, we shall be uploading item 7, and that will be a paper complete of Jjeb. Then please, you may consider putting in the comment section which mock body do you think we can discuss next. Yeah, of course, put that in the comment section. That will work for us better. Which mock body do you want us to discuss and which subject, by the way. Alright, so without wasting time, I think let's get there. Okay, good. Now we are in for Jjeb item 6. Without wasting time, let's go there. So the saying, let's read slowly. The saying, in your area, many households rely on electricity but often face power outages. Now, power outages is like, of course, I know we all use electricity. That time when there is a total blackout, there is no power. That's the common language people use. There is no power totally. All right. So maybe due to a failure in the transformer or anything, and the high electricity bills because of unsafe wiring and lack of knowledge on how electricity works. Oh, sorry. The residents have noticed that connecting wires get very hot when operating on electricity and wonder why this happens. Shall explain. They also complain that their devices get burnt because the electricity from the power lines comes at very high voltage and must be lowered before it reaches homes. Oh, they need to lower it? Alright, good. But of course, if you look at electricity from the power lines, which is at a very high voltage, lowering it, you must be thinking about which device do you think we use. Be thinking about it. We are going to bring it next. Okay. Many families struggle to understand their monthly electricity bills. Yes, a common habit. And how different wiring parts in their homes help protect them and keep power flowing safely. Anyway. Alright, so let's go and see the next part still about this. Okay, good. Now in here they're giving us the hint about this equation. So they're saying hint, Dodoviko, oh, I don't know which tribe is this. Dodoviko has a fridge rated 7.5 ampere, 240 V, 8 light bulbs each rated 4 ampere and 5 ohms, and 3 smartphones each rated 4,400 milliampere, 240 V. We shall explain what this means, what this really means. But maybe just to give you a brief info is that whenever I saw it written like this, a comma, this one with the V, it means that when connected to a 240 voltage source, it supplies current of 7.5 ampere. I don't know whether you really see that. If connected to a resistor of 5 ohm, it will be able to supply the current of 4 ampere. If connected to a phone, if connected to a 240 V source, it will supply a 4,500 milliampere. Of course, you have ever seen this on your phone batteries. I guess you have ever seen this. Okay. Each unit of electricity is equivalent to 1 kilowatt hour. So each unit of electricity is equivalent to 1 kilowatt hour. Okay, we shall get into that. Task is the saying. Remember number 1, part A. Carry out a scientific investigation to show how voltage across the devices is related to the current through them. How is the voltage related to the current? Shall be seeing that. Remember number 2. Explain to the villagers why connecting wires become hot when operating. Part B. Identify the device used to lower voltage and describe how it works and the importance of lowering voltage. You must be thinking about something here. Part B. Which device do we use for lowering voltage and where? Be thinking about it. However, we shall get there. Part C, the saying. Help Dodoviko understand the meaning of the rating. Oh, we have it forward here. Understand the meaning of the rating 7.5A. Okay, we should help Dodoviko. But I know not only Dodoviko, including the person watching this video. Yes. Anyway, sorry for that. It's just a simple joke. So help Dodoviko understand the meaning of the rating 7.5 ampere, 240 V. Alright, please, if you're a teacher or if you're a candidate or a semi-candidate, you need to watch this video to the end. There is always a learning point. Never watch a video halfway. Part C, Roman number 2. This is maybe Roman number 2, I think. Establish the cost of 1 unit of electricity if in a month Dodoviko pays a total of Uganda shillings 121,050, for which a fridge operates 4 hours every day for 15 days, each bulb for 12 hours each day for 30 days, and the phone spend 1.5 hours charging every day for 30 days. 30 days means a month, if you can really think about that. 30 days means a month. Okay. And even here, they've told you that Dodoviko established the cost of 1 unit of electricity if in a month, Dodoviko. So a month has 30 days according to what you're saying here. Part D is saying, identify the common house wiring components and explain to the villagers how each protects them. Alright. We shall be getting there. Let's go to my number 1. We get there. Now, in this formula number 1, I want to look at this. They're saying we should, okay. They're saying that carry out a scientific investigation. Now, a scientific investigation may have a number of stuffs. In here, you can carry out a scientific investigation must involve must involve what we call what? An experiment. A scientific investigation must involve an experiment. But again, in an experiment, what will you need? In an experiment, what will you need? You need, of course, the apparatus. Some people call it that. You will need the apparatus. In an experiment, you will need, okay, to give us a diagram. Of course, you just describe the villagers to give us a diagram. Then also you must tell us a procedure in this experiment. Then you must also tell us the conclusion, like what is the way forward about what you have asked, if you can really think or figure out on that. Now I'll pick another ink. Here they say, carry out a scientific investigation to show how the voltage across, to show how the voltage, allow me call voltage to be V, across the device is related to the current. So voltage and current, how are they related? In simple terms, they're asking, if you have voltage and you increase voltage, what do you think is going to happen to the current? That's what you want. When you increase voltage, what do you think is going to happen to the current? And if, do you really see that? And if you reduce the voltage, reducing the voltage, what do you think is going to happen to the current? That's what they want here. And to come up with this, you need what we call an experiment, which you're going to carry out right here. And an experiment, we need the apparatus. But first of all, the apparatus we shall need will be the ones which can measure what we have so far. Which apparatus is used to measure voltage? It is a voltmeter. Which apparatus is used to measure current? It is an ammeter. So you see that? So we shall need a voltmeter and ammeter. But to have a complete circuit diagram, somewhere, since you're talking about V and I, at the back of your mind, you must recall this formula that V is equal to I, R. So if you have V and we have I, you shouldn't forget what? Resistance. You see that? We need it. And of course, all these are connected in what we call a circuit. Are connected in what we call a circuit. Now in a circuit, what will you need? You will need a switch. Do you really see that? So circuit, we shall need a switch, we shall need a voltmeter, we shall need an ammeter. Which device do we use to measure resistance? We call it a resistor, like that. And I think that's all what we need right here. Now let's go and have part A, Roman number 1 answered. It is simply an experiment to show variation of V and I. When increased voltage, does current increase? When decreased voltage, does current decrease? We don't know, but let's go and look into that. So first we shall begin by, okay, getting there. Let's go and see how this we can get responses for this. Now first you need to know, like I said, you must tell us in your investigation what are you going to use. Now in our investigation, Roman number 1, first of all we shall need the materials. So materials needed. So we're getting our materials which we need. The materials needed, you see, I talked about, oh well, in the circuit, of course, we must have connecting wires, we must have a resistor, we must have a voltmeter, talked about that, we must have an ammeter, one is enough. We must talk about dry cell, the source of power, I forgot to talk about that. We must have a switch, then we must have a rheostat. I will explain what these all mean. But then, before we go there, maybe you may also need to carry out this experiment just at home or even at school, locally. Let's go and see these apparatus here in real life. Let's go there. So now here you realize that we have our apparatus, and what you have here, you see a letter A here, that's an ammeter. Simply, that's our ammeter. Then you see letter B here. All right, I guess you're seeing it. That's our voltmeter. I will not talk about this. You really know that. And of course, I know this one, tiger head, is indeed very, very common. So that's our cell. The next, this one, you see ohms. This is our resistor. This is our resistor. Now this one is what we call a rheostat. A rheostat. Now I'm going to explain something here. A rheostat. Then this one here is our switch. This one here is our switch. How does it work? You get this knob and you make this hole metal to enter into this hole here. It comes and enters here, then it will complete a circuit. It is the switch we use here. Well, I know in the room or where you're watching this video from, you have got a switch on the wall. It is a bit different. This is a laboratory switch, and these are laboratory ammeters. These are all laboratory apparatus for just carrying out this experiment. In real life, the game changes a little bit. Of course, we can't use that ammeter. This one can't be connected to a 3-phase. It will just have to burn out. Okay. Now, still about this, let's proceed. Now, this is our ammeter, voltmeter, our cell. Don't call it tiger head. It is a cell, a dry cell. Okay. Now, this one is the the EMF source. A switch. Now we have, now these two are related. This one here, a rheostat is also a resistor. Then this one here is a resistor. Is a resistor. Even this one here is a resistor. Now I know you're wondering, of course. Now, but with this resistor here, you realize that, okay, with this resistor here, you realize that it comes when it is labeled like this resistor is saying here, it has only 1 ohm. Then you can have another one with just 5 ohms. Now in this experiment of ours, they specified. You see here, this experiment of ours, they specified. They said there is one standard resistor. Standard means a resistance must be known. That standard resistor must be of 5 ohms. Now it's that black thing we're having right here. It's that black thing we have right here. You can really see this. That's the resistor we want. Now we have put 5 ohm, but 1 ohm, but it's meant to be 5 ohms. Now a rheostat is also a resistor, but what happens is we move this knob. Now with this rheostat here, you can set any resistance you want. This rheostat, you can move this knob here, and you mean to have, maybe you can start from 0 ohms, you go to 1, you go to 2, you go to 3, you go to 10, you go to 15 ohms. So this one here is a resistor which can be changed. You change the rating by moving this knob. You can change the rating and maybe put a rate at 15, you put a rate at 5. So it is a variable resistor. It can show any resistance. This one here, it can even give you 0 resistance. Okay, this one here is the fixed resistor, doesn't change. This one is fixed, this one changes by moving it. Maybe where it is there, it is at maybe 10. I'm giving an example. And when you move it this side, I'm giving an example, please. Maybe it is 20 ohms. And when you come this side, maybe it is 5 ohms. And when you come this side, maybe it is at 0 ohms, I'm assuming. So you can move this knob up to here with 0 ohms. When you move it up to here, 5 ohms. When you move it here, 10 ohms. Please, these are just imaginary values to help you understand. Not really that's how it goes. Then when you move it up this side, you have 20 ohms, meaning that you can easily move around changing the resistances. So resistor, fixed resistor. This resistance can be changed. Okay, this one is a switch. And now with that, what does it mean? Okay, we need to have this apparatus arranged in what we call a circuit, a complete or a closed circuit. Let's go and see how we can draw these other stuffs in the circuit. Let's go there. So to begin with, we begin with our connecting wires. Next, we have put our resistor. This is our resistor R. This is our resistor R. Okay, then next we are going to have our rheostat put right there. Our rheostat, you will see how the symbol for rheostat. Okay, so this one is our rheostat. It must be labeled like that. That's our rheostat. We have named it for you. That's our rheostat. Now this is how you must always draw a circuit diagram. If I told they bring a question to do with relationship between voltage and current. Now we are going to have our switch K. We're going to have our switch, and we shall label it letter K. Okay, the next we're going to have our cells right here. We have it drawn. You must use a ruler. You can some also using a ruler. Okay, we have our ammeter here, our ammeter right here, and we shall call it A. Our ammeter, we shall call it A. Then next we must come and have the voltmeter right this side, and we shall call it V. Okay, good. Then we have this completed. And finally, you look into that, you realize that we have now our complete circuit. Look, this is the cell, the tiger, you saw the other side. A switch, you saw it. A rheostat, you have seen it in real life. However, the diagram must appear like that in a circuit. A resistor is this one. Now, this one here is the resistor where you were seeing 5 ohms. This one here, a rheostat, is also a resistor, but it can be changed. We have a voltmeter right there. We have an ammeter right there. But then, as a student, what must you look into? What must you master right here? About this diagram, you must make sure that the resistor, this voltmeter is connected across the resistor. They must be like this. It is very wrong to draw like this, then you put an ammeter here. Be careful. In fact, what you must know is that the voltmeter must be in parallel with either this resistor or with the dry cells. Must be in parallel. Parallel meaning if current is moving, if say for example current is moving, when current reaches this level here, it is divided. Maybe assuming it is coming like this, the current is coming like this, part will go this side and part will come this side. That point where current is divided, we call it is in parallel or a junction. So this voltmeter must either be in parallel with a resistor or a dry cell must be connected across. In fact, the arrangement must be like that. If you can really look into that, never to change. This ammeter, you can put it anywhere. The ammeter must be in series with the dry cells. How that really makes some bit of sense. Now, in your procedures, what are you going to tell us? Just simply talk about what you have here. Remember, here we are talking about the V and you're talking about the I. Now we want to see how this is related to that. Now remember, I have the voltmeter here, we have the ammeter here. So what you're going to do here, you will tell us that maybe the circuit is arranged as shown above. Maybe in simple, okay, I can just give you a simple intro here. The circuit is arranged above. Then we say when switch K is closed. Now what happens when switch K is closed? Current start moving. Okay. Then when the switch K is closed, what will happen here? You realize that and the rheostat is adjusted. You adjust the rheostat what you want. Remember, this one is originally 5 ohms. Now you can change the rheostat maybe to 10 ohms, like that. Okay, what will happen? This voltmeter, we shall have a voltmeter reading and ammeter reading. We shall have our table like this, like that, like that. Okay, now I have the voltmeter reading and I have the ammeter reading. I. Voltmeter, I is current and V is the voltmeter. Now, first, when maybe I'm assuming when the resistance on the rheostat is 10, the ammeter reading maybe is 2.5. Okay, I don't want to use values. This will really bring problems. It will bring serious problems, you guys. I'm really sorry for that. So maybe in level 1, we have the voltmeter reading and ammeter reading. The note shall do again next. We shall now the work we change. We keep changing this. We now adjust the rheostat and maybe it goes and shows 15. Sorry for that. It maybe shows 15 ohms. 15 ohms will give us another voltmeter reading and ammeter reading. We again change the rheostat reading to maybe 20 ohms. Voltmeter reading, ammeter reading, you note them down. Next, you are going to plot a graph. Now this one is a table of results. You're going to plot a graph. After plotting a graph, that graph will appear like this. You can do this experiment at school. That graph will appear like that. Whereby here you have the voltage, here you have current I. And what does this graph mean? This graph means that an increase in voltage leads to an increase in current. As simple as that. However, let's go and look at this in details such that you can really see which ones you must write. Okay, so let's get there. So in the statements here, shall say, okay, we say I've talked about this switch K is closed for current to flow and the rheostat is adjusted to some given value of the current. Okay, to some given value of the current I as seen from the ammeter. Of course, you'll be seeing the ammeter reading right there. Okay. Now, after noting the ammeter reading I, then the voltmeter reading V is also noted. You see that? Good. The experiment is repeated for different values of I. For different values of I. Of course, that is done by when you adjust the rheostat, the I also will change and even the V will change. I is the current being used. However, the voltmeter is helping us to measure how much PD of voltage are remaining with. Now, you repeat the experiment. The experiment is repeated for different values of I, like we clarified here. Okay, the experiment is repeated for different values of I. Now, different values of I, you saw the other time I drew. Each column where we go, it means that we have repeated the procedures. You saw me drawing this back then. Okay, the experiment is repeated for different values of I, obtained by adjusting the rheostat, and the results are tabulated. Tabulated meaning this: we have current I here and voltmeter reading there. Okay, a graph of V against I, this is what they are meaning. A graph of V against I is plotted, which gives a straight line through the origin. Yeah, I do that for you like that. This implies that V is directly proportional to, now this symbol means directly proportional, and directly proportional means that an increase in I leads to an increase in voltage leads to an increase in current. The more the current, the more the voltage. The more the voltage, the more the current. Anyway, hope that makes some sense. This indicates that the current flowing through the electrical devices is direct. Okay. We can just say directly proportional to, I don't know which language you can use right here. Directly proportional to, all right, the voltage. But of course, you know that a dry cell gives us what we call a DC voltage direct. Okay, it gives us direct current. Okay, good. So with that, and without wasting time, let's, I think, proceed. Now we have part B, the other part, Roman number 1, correctly and perfectly answered. Let's go and look at Roman number 2 without wasting time. Let's go there. So back to the question. Now let's look at Roman number 2, part A. Roman number 2, part A. Roman number 2, part A. Without wasting time. So here they're saying, explain to the villagers why connecting wires become hot when operating. Yes, you ever seen this? Even when you're charging, your charger becomes hot, or even your phone becomes hot. Why do you think this happens? We got you covered. Let's go there. So in order to look at this, we must quickly reason out on this. So realize that as far as this is concerned, let's go there. Now we have it in Roman number 2. Our Roman number 2. Our Roman number 2. Let's go there. Now we shall first of all go pictorial, such that we can really understand this. Why do electric wires get or become hot? Okay, now we have our dry cell, we have a bulb, we have our switch. You saw this in some pictures in the first part. Now, when the switch is closed, of course, just know this bulb is lighting and current is moving into these wires here. But of course, before you think about current, you must think about these small things here, which you call what? Electrons. You must think about electrons moving into the wire. So then after thinking about the electron, just know that the wire we are having also has got particles. Now, why do these wires become hot? Think about this. You can get your hands, put them together, and start rubbing them in opposite direction. Do it while increasing the speed. What do you really feel there? I guess you feel some heat, and that's what happens here. That in here, the friction between the electrons from the dry cell, or the electrons and the particles in the wire, of course, maybe it may be a copper wire, which are solids, and you all know that from the kinetic theory of matter, particles, solid particles have got, in fact, a solid has got small particles in it. I don't want to go into deep chemistry here. So those particles here, as they collide with the electrons, the friction between the electrons moving, maneuvering all through the particles causes the heat. Say for example, this wire, we have it zoomed right here. Inside the wire, these are particles of the wire, and now this one here is an electron. Oh, use some different ink here. Now this one here is our electron. Look at this. So erase this off. So now this one here is an electron. If you can really look at that, this one here is a particle inside the wire. Please, what you're seeing here is our wire. We have zoomed it. Now as this electron is coming, moving past the particles inside the wire. Now this picture is only trying to show you what happens there, but don't think that they are spaced to this format. So the friction between this electron and these particles of the conductor, that friction, what do we mean by friction? Try rubbing your hands together. Rub them really hard. Do you feel some heat? That's what happens here. So that heat here is what you feel when using an electrical wire or an electrical device. That's why they become hot in the long run. Or if you don't happen to understand that version, you can have it this way. No worries. Now still, we know that. Alright, so another version here we can have is that, like, in fact, that version can really make some sense, but we shall use this also. That, now guess what? Assuming this particle is moving at a very high speed, and this particle knocks this, what happens is, when this electron, which is moving at a very high speed, the electron, when I talk about electron, think about current moving. When the electron comes and knocks this particle, maybe there are very many, another comes from this side, knocks it right there. What will happen? This particle will be forced to slide and move. The particle will be forced to slide and maybe moves up this level here. You see that rotated stuff? Like that. Now, the friction to force this particle to move from here up to here is the way you do. Versus, remember, also other particles are here. Now, if this is one pushed, even other particles are here. As it rubs with these other particles here, it will cause some spark-offs. In fact, due to friction, heat will be generated. So you can talk about this particle here having kinetic energy, of which when it knocks this one, the electron loses the kinetic energy, and kinetic energy will be given this other particles of the conductor, then onto this like that, and the device will become hot. All right, so I think you can really look into that. So you can talk about it in a kinetic energy version. This electron is moving, knocked this particle. That the process of the particle wanting to move slightly. Well, the movements here are not so big. It can just be very minimal, but just know any slight displacement causes some heat to be generated. And remember, it's a continuous process. As that is happening, they are knocking another particle here, they are knocking another particle right here, knocking another particle, and the same thing happen. Knock this, knock that, knock that. Then that little heat is generated, and you feel it as real heat on the outside of the wire. Okay, hope that really makes some bit of sense. Let's go and see how this can be explained theoretically. Okay, so without wasting time, let's go there. So they're saying when power is switched on, let's get there. When power is switched on, electric field is set up in the wires, meaning the electrons, of course. The electrons in the wire are accelerated by the field, thus gaining kinetic energy. Yeah, now the kinetic energy, they're calling it KE, but if you're a student, don't use this kind of writing. Don't abbreviate. Okay, as the electrons move in the wire, of course, this is where we are. As the electrons move in the wire, okay, they collide with the atoms. Which atoms? Atoms of the conductor, which is conducting that current. Atoms vibrating about their fixed mean positions. What I was meaning is the other displacement, which is very, very small, more like from here and up to just right there, very small. That's what I mean by mean position. More like they've not even left their position. Vibration is meaning that displacement, okay, and lose some of their kinetic energy to the atoms. Yeah, they are meaning the electrons which were once moving knock the atoms. The atoms are sent into motion, while the electrons will lose their kinetic energy in some extent, and in the so doing, the heat will be produced. Here we go. The atoms then vibrate rapidly with larger amplitudes, and as atoms rub against each other, talked about that, heat energy is produced. I've really explained that. This increases the temperature of the wires, making them hot. Hope that really makes some sense to you. All right, good. Now let's go on. We have part element number 2. Let's go and look into part B. Without wasting time, let's go to part B. Okay, in part B, we're going to look at this. So part B, here we are. The rest of that, we have part B. Let's go right here. They're saying part B, here we are. Identify the device used to lower the voltage and describe how it works and the importance of lowering voltage. Now, which device do we use for lowering voltage? Of course, good news. I told you must be thinking about this as we are moving forward to finding out the solutions to this. Now, of course, guess the device by just writing those two letters. Another one. You can really think about it. That. Okay. All right, here we go. So it is a transformer, but again, we are worried. We have what we call a step up transformer, and we have what we call a step down transformer. The description is more like the same, but there's something unique. Let's move on. Now, about a step down transformer, what must you know? About a step down transformer, what must you know? What must you know about a step down transformer? Let's get right here. So we are saying that the device okay, now simply here we are telling you that the device, look, the device used for lowering the voltage is called a step down transformer. Think about this word down. Whenever they say lowering, you say down. If they say increasing, you use a step up. However, I will explain what these two really mean right here. Okay, let's have our transformer drawn first of all. However, now our transformer in real life, this is how it looks like. This is how a transformer looks like in real life, though we are trying to get it here. If you're using a pencil, you can draw like we're having it right there, because here it becomes a bit complicated. The one you can draw in your exams is the one you're having right just there. Please, I request, or you must always use a ruler when drawing this. You must always use a ruler. Now, let's get our transformer drawn first of all. A step down transformer, and it is in this video that you will come to understand the working of the mode of operation of a transformer, and why do we even use transformers? Are they even useful in any way? We are going to look into that. Okay, so we are doing a transformer. Please, I've told you, you must also be using okay, you must also be using a ruler to draw this. You must also be using a ruler to draw this. Okay, now I think without wasting time, let's get there. We have it drawn. Let's have our transformer drawn. Please, as we are drawing our transformer, please, I remind you to subscribe to the channel. Subscribe to the channel such that you don't miss out watching the next videos. I told you sooner or later we shall be making this channel specifically for our subscribers, and whoever is not subscribed, it will be no more, where you will need to pay before you access the videos here, though that is not my intention. So better subscribe before even you complete this video. Pause and subscribe. Of course, there's only appreciation you can give back to us if you really look into that. It is the only appreciation you can give to us, simply. All right, so let's get our transformer drawn very fast, and we see the way forward. So when you're drawing, you must also draw like that. You must also draw your transformer in that format. You must also draw your transformer in that format. You must have your transformer drawn in that format. Those are our turns. Okay. All right, so let's get there. Have this drawn. That's what we call a primary coil. That's what we call a secondary coil. We shall get all this explained. I know you have ever come across a transformer, but at least I know with this you'll have something new to at least understand in this video here. Please consider sharing this video. Okay, I appreciate whoever takes time and shares this video to some students out there, so that they can also get exposed, or they can come to know what happens. Okay, as far as answering these scenarios are concerned. Now, here we are in for a step down transformer, and then this is an example. Now, looking at this picture, what do you see? Look at these wires, which are, allow me use the word tying, but it's meant to be, okay, allow me use the word tying for simplicity. So the wires they have tied here, and the other wires they have tied here. Now those wires there, we call them turns. And we use a symbol capital N. Now look at the number of wires here and the numbers of wires this side. That's where our video is going to begin from. Now to call a step down transformer, it should be that the number of coils in the what you call coils are these things here you're seeing there, or what you're seeing right here, coils. So we have a primary coil and we have a secondary coils. The secondary coil, the other ones here, primary coils are here. Now, if the primary coils are more than the secondary coils, then you call that one a step down transformer. Now, how does this transformer work? This is this side. In fact, a secondary coil, of course, you all know that primary is where you begin from. So primary is where you receive the power from the umeme. This primary here is the umeme people. Allow me to use this for better understanding. Umeme. Now, this secondary here is what you use in your homes. Okay, when charging your phones in your homes. Now, what does it mean? It means that for us here, in a step down, it means that the power from umeme comes when it is a very high voltage, but in the homes we need little voltage compared to the one direct from umeme. So we need a step down transformer in that process. What about if, say for example, we have very many homesteads, and the power which is coming is the voltage which is coming is not enough. Then they shall need a step up transformer. Step up means that there will be more coils in the secondary and less coils in the primary. Hope that really makes some sense. Maybe also to make you understand this here, to make you understand this is that this one goes into our homes. You see that? Into our homes. So it means that what we have, the number of turns we have here, matter a lot. Like, we aim at either reducing the number of turns here, that is a step down. If we increase the number of turns here, that is a step up. Okay, hope that really makes some sense. But again, before we go into that, let's first of all, again, go pictorial. And we see the way forward. Okay, so looking into this, let's go and see the way forward about these transformers here. Now, a transformer, what you must know is that regarding a transformer, you must be knowing this. A transformer uses, now, a transformer, we have what we call alternating current and direct current. How does alternating current work? An example of alternating current is the charger you use at home, the sockets. Of course, you can sell phone charger here. That's an example of alternating current. Then example of direct current, those are the batteries you use. The batteries in your remote. Okay, we call them direct current, of course. Now let's look into the, alternating current. Now alternating current goes in the way that current can come like this, in that wire, move like that. Then it comes back like this, comes back like that. It reaches. Then again, it comes back in this very lane. You see how fun it is? Like that. Goes back this side, and it comes back like that. Again like that. That's why they call it alternating. It keeps on changing. It goes, comes back, goes, comes back, goes, comes back. That kind of description, but just know it happens at a very high speed. I know that I'm surprised. How is it alternating? Anyway, just take it like that, that it keeps on changing direction. While direct current, with it, current from here, of course, we just go, maybe this one is here is a positive, this one is a negative, this one is a positive. Guess what will happen here? The electrons will move from here up to this side. Those are electrons. Electrons E, from positive to negative. Those are electrons. Then current will come from this side, going like that in one direction. So it means that in this context here, allow me to wrap up this. Here, if this is our negative, current will move like that, and again come back this side. That's how it goes. Meanwhile, this, it can go like that, up, more like a DC, like that, pass via this, downwards. It comes like that. Okay, that's phase 1. Phase 2, again, comedy happens here. Some bit of comedy anyway, though you have to bear with the truth. So here, okay, this one for us. I don't know. Let me use some link here. So again, as it has come like that, again, current will move like that, upwards. It has changed direction, like that. Again, up, again like that, back here. Again, the other process happens, to and fro. Of course, I have red, and yellow. So it is red, yellow, red, yellow, red, yellow. We call that alternating current. This one called direct current. I've explained. Now, an example of examples of transformers in real life. You have all ever seen the laptop chargers. They have that we call it an adapter. That box-like stuff which has that green light, which gives like green light here or red light in some laptops. That's an example of a transformer. Okay. Then also, you ever seen these other transformers here? But of course, we used to have this kind of transformers back in the 90s. Nowadays, we don't have them. Now, in the modern world, these are the ones we have. Though, in some parts of Europe, they still use some of these transformers here. But in Africa, they're very rare. So, commonly in Africa, we use these mega transformers here. All right. Now, that's what we mean right here. Now, you see, the one of the laptop gives very little. Okay. Now, let's go and still look into this about a transformer. We must know, how does a transformer work anyway? Let's go there. Now, one would ask, do we even need a step-down transformer or a step-up transformer? Yes. Let's look at this. Now, this is our power station. You can see the buildings there. Just see how cool they are. Okay. So that's our power station. Now, just know that if this is a power station, from here up to here, so the electricity must move from here up to right there. Like in Uganda, we generate our hydropower from Jinja. For those who know where River Nile is, or those who have crossed the bridge, just right in that place, there is where you get our electricity from. And guess what? Where are you watching this video from? Maybe Kampala, maybe you are watching it from Gulu, you are watching it from Soroti. How does that power reach you? Now, just note, as this power moves long distances, the voltage goes on reducing. The voltage drops. So you realize that as the voltage drops, what really happens? Let's look into this. In our homesteads, we need a power supply of 240 volts or 120 volts. That is the power supply we need, by the way. But this 240 is commonly used in United Kingdom, England. Yeah, people in England use this kind of voltage here. Why? This 240 voltage, now this one is just more information, not really examinable. This 240 voltage supply works on what we call a three-phase in UK. This is the kind of, they use three-phase. Even in connecting in buildings, they use three-phase. That's what they use, and that's why they use 240. Even some parts in Uganda, of course, you know Uganda, we welcome anything. So you adjust restriction according to what you have. So even in Uganda, but in a country like America, they have less than that. They have either 230 or 120V. Reason, in America here, they use what we call two-phase way of connecting wires. I don't know if you understand that. Now, what is the importance here? The importance here is that these ones with the 240 voltage with three-phase, they are the ones you can use for cooking. The ones you can use for cooking, in fact. But this one here, where I use two-phase, like in the US, it cannot all that be used. Though in some parts of the US, still some people maneuver and use this in the long run. Now, why do we need a transformer is our question here. So, from this up to your home, the longer it moves, the lesser the voltage. The voltages go on reducing due to very many factors, by the way. Factors like temperature, in simple terms you can call it weather. Okay, factors like temperature, you can call it weather, like that. Then, do we need a transformer? Yes. Then on another way, what if now I know, you are thinking about this. Now what if when my homestead is just right near these people here? What happens? Now you just imagine the 1200 voltage. Remember I told you that your home need is only 120 or 240. What if when this 12,000 voltages come into your house? In fact, if you ever watched a movie, I want to tell you what this really means. If you ever watched a movie, you ever seen when a bomb blast, in simple terms, okay? That's what can happen. In fact, the building will just burn down. No appliance in your house can hold this 12,000 volts. These are 120 volts and 240, the ones you need in your house. But here, 12,000 comes direct. What does it mean? Your building will be burnt. Now, how can we solve that problem of excess voltage coming into your house? We need a transformer. How can you solve the problem of very little voltage reaching your house and it cannot even power up your TV or a refrigerator? We need a transformer. That now brings us to a step down and a step up transformer. Why step down? We need a step down transformer. Now look, from the power station, we need to take these voltages here to what we call a step up. Allow me use the word up. There is a step you connect it there. This is the step up. Now this step up transformer here, we increase these voltages here, step up to even maybe, say for example, I'm just giving an example, 20,000 voltages. This one will be connected to the electric poles. Never joke with the electric poles, especially the ones I put here. These ones, I call them pylons. Please never joke with pylons. It's just way more deadly than what you can think. Okay, now, so a step up from the power station to a step up. Step up increases the voltage to the pylons. Why that is because these pylons here move very long distances. And in some areas, you realize that these pylons, once you see them, do you even know that Uganda supplies some electricity to Kenya and they use these pylons? Yes, they can carry very high voltages. But how are they able to do that? The step up transformer helps to boost up the voltage so that it can move longer distances. Now, as it is coming, maybe as it has moved from here to here, maybe I think of this is maybe power station in Jinja, this is maybe in Mukono, this is maybe in Soroti. Just now by reaching there, it has reduced on its magnitude. Again, it is given to another step up transformer. Step up transformer to boost the voltage again. The step up transformer to the electric pole. Electric pole has another transformer on it. You ever seen them? Now that is our step down transformer. The step down transformer will step it down to the required value. The required value in this house. Then that step down will give us this required value. Up in that story, I've now understood why we need transformers. Then next, how do transformers work? Please, here we just understanding, not cram work. Alright, good. Without wasting time, let's go and look into this straight away. Now, the story begins here. Alright, since you have known what transformers mean here, let's go to the man whom we call Faraday, which we call Faraday's law. Now, Faraday tells us that the law, Faraday's law of electromagnetic induction, states that a changing magnetic field induces an electric current in a conductor. That a change in the magnetic field induces a magnetic current, electric current in a conductor. I hope you can really think about that. Say, for example, if you have a magnet right here, and you have this magnet here, then we keep on rotating this magnet in that order like that, in this order like that. When you rotate this magnet here like this, you rotate it at a very high speed. The theory says this magnet here will induce current. Current will start flowing through in this conductor in a way that this ammeter here will be able to give you a reading, or it will give a deflection. I don't know if you're figuring out on that. So when you go on changing this like this, you change this magnet near an electric wire. When you change the magnet, this is what I'm saying, that a changing magnetic field. A magnetic field is this. Please, you must understand this before you go to the transformer. Now, magnetic field moves like this. Like this. From north to south. From north to south. That's a magnetic field. Now, when you turn it around, it comes here. Okay? When you turn it around, what does it mean? It means that once you change it north-south, when you rotate this in this order, whereby at a certain point, maybe it will become south-north. Another rotation, north-south. Another rotation, south-north. But in this very position, current will be induced into these wires here. Current will start flowing into these wires here. That's according to Faraday. Science is more like, it's very enjoying, by the way, very enjoyable. So now, as this current is flowing, it will show a deflection here, verifying Faraday's law. I don't know whether that really makes some sense. Now, you must bear in mind that before you go to a transformer, is that any change in current leads to a generation of, and in fact, any change in magnetic field leads to a generation of electric current, or still the vice versa, or the reverse is true. Any change in current leads to a change in magnetic field. Alright, good. Now with that, let's go and look into this. Let's go and look into this. We want to know how the transformer works. Okay, we now get onto this guy. Now, our story begins from here. What you must know is that from the electric wire, from the charger, okay? Now, imagine this is the power station. This is now maybe our transformer here. Whereby transformer here, this is the primary coil, you can see that. This is a secondary coil. Step down. Reason, the number of coils in the primary coil are more than number of coils in the secondary coil. Now, what does it mean? From Faraday has told us that any change in current leads to a generation of a magnetic field. Now, look, as current comes, remember this one is an AC current. Current comes in the first cycle, goes like this, passes through the wires, passes through the wires, passes through the wires, like that, like that, like that, like that. Back there. Now remember, it is an AC current. I explained this. If it is an AC, think about this. Again, the current comes and follows this direction. The current comes back, follows like that, like that, like that, like that, like that, via this, back there, like that. Now, are you saying that current has changed direction? Yes. Current has changed direction. You have this arrow, this journey first, the journey from here up to this side, that was the first journey, and also that part when current is changing direction from here again to this side, like that arrow. Now, that's what is happening. Now, just bear in mind that current is changing direction. Then what you must know is that for any conductor, imagine that is a wire, and we allow current pass through this wire here, current pass through this wire here from, okay, laws of magnetism. This wire here will be, okay, will be magnetized. In fact, this wire becomes a magnet in a way that one part can be a north pole and the other part can be a south pole. That's what we know. But remember, even here, so the current which is moving in the first cycle, like this arrow here, there will be some, okay, magnetic field generated around it. Now, magnetic field in which way? Look at this. Maybe in the first case, this is what we have. The magnetic field will be like this. This will be south, and this will be north. That's how the magnetic field is moving. That's for this arrow. But again, if the arrow changes direction in this order here, allow me to use red ink for that area. Red ink. Again, the magnetic flux will move like this, back down, coming out like this, coming out like this, because of change in current. Any change in current leads to change in the magnetic field from Faraday's law. Now, what does it mean? Originally, it was north, south. Change in current will give us south, north. Now, that process whereby the poles are changing, we had north up, south down. In another cycle, north down, south up. That kind of changing in current, changing in magnetic field, will make this magnetic field to go on increasing, and that magnetic field, the magnetic flux being produced here. Remember, once you have a nail here and you put a magnet, then another nail is at this distance. I am aware that there is a force of attraction even when these things are not in contact. By the induction means there is nothing in contact. So it means that here, since this coil is here and is already magnetized north-south, even this coil in the secondary coil will be magnetized in a way that what happens this side also happens this in the secondary coil, meaning north up, south down. Again, south up, north down. Now, but Faraday told us that the change in the magnetic flux leads to uninduced current. So, as the change in the magnetic flux will happen, there will be an induced EMF into the wire here. So this wire also will gain current, which current will flow into the house. Here we're using our phone simply. You see that? That's what I want to see. Now here, the step down reason, you have 200 volts, but you are giving out 4. That's what I mean by step down. So in simple terms, or in summary, what really happens right here is that the changing current leads to an introduction to a changing magnetic field. A changing magnetic field will induce the magnetic flux will induce a magnetic field in the secondary coil also, in a way that there will be a change in poles north-south, south-north. In the so doing, there will be an induced EMF. This EMF is the total voltage V, but from V is equal to IR. The voltage produced can give us the current I, which can flow into the phone. Do you really see that? Or if it is the voltage needed in the house, we can easily step down the voltage. Mark the following things. 1, changing current. Next, leads to a changing magnetic field. But a changing magnetic field can bring an induced current, and that's what we use. Okay. Now, I don't want to go into what we call Lenz's law. This is what we call Lenz's law. I don't want to go into it. What I've explained really brings this near to you. Let's go and see this in writing. I've tried my level best to have this explained. Transformer work is a bit super technical. So let's get there. So the same. When an alternating voltage moves through the primary coil, it induces a varying current which flows through the coil. Of course, remember, voltage is the source where voltage is the source where you plug your charger, or from the voltage is from the pylons. Now, the voltage, it is from, now, once you have voltage there and have a wire, this voltage here is more like a battery which will give us the current. What flows is current, but the source is the voltage. I don't know if that makes some sense. Okay. Now, when an alternating voltage moves through the primary coil, okay, it induces a varying current which flows through the coil. Varying means that the other changing of current which I've explained. Next, let's go there. They're saying the changing current induces a changing magnetic flux in the primary coil. I've explained that the flux, those were the lines you were talking about. But remember, the magnetic flux is this. Let me just put it for you here. This is the north, this is south. This is what I mean by magnetic flux. Like that, Of course, you were drawing, some teachers make them be very many, like, but they don't intersect, please. I know that the stuff I'm using can't make them straight, so like that. Now those lines you're seeing there, we call it a magnetic field, but a combination of them we call it a magnetic flux. So the changing current induces a changing magnetic flux in the primary coil. Now remember, it's on the primary coil having. Now it's going to move from the primary coil. This flux will go on expanding. Like, say for example, we have a primary coil right there and have a secondary coil right here. Now what does it mean? This flux here will go on expanding until when they will affect the secondary coil. That's in the next part. Let's go there. And the last one. There are only 3 steps here. So you're having the changing magnetic flux links up with the secondary coil with less turns. Remember, once the turns are very little, then even the voltage will be very little. I explained that, which induces a lower voltage in the secondary coil. Now, if it was to be a step-up transformer, you would say, which induces a magnetic flux which links up with the secondary coil with many turns, which induces a higher voltage in the secondary coil. It only changes from here. When you want to step up, it changes from here. More turns, which induces a higher voltage in the secondary coil. Now, this number explains 2 numbers in one: step up and step down transformer. Then in your diagram, you must now have this. In your diagram, you must make sure that if you are on a step up, in your diagram, you must be having less turns here and more turns here. More like this, like that. So here you can have those turns like that. Then in the secondary, there must be very many. You can see that. Now that will be a step up. Same description, but they only change from right here. They only change from here. Okay, sorry. They only change from here. I'll clarify this for you. Hope this makes some sense. More turns, which induces a higher voltage. The more the turns, the more the voltage. The lesser the turns, the lesser the voltage. Hence, a step down transformer. Maybe what I didn't show you here was about this magic which you had right here. Please, this is what they use, the mechanism they use in what you call the wireless charger. You ever heard of phones having a wireless charger? So a wireless charger uses this. Whereby they will get a secondary coil and they will insert it into the what? Insert it into the phone. Then the primary coil, they put it inside the charger, which you plug into the socket. Then this one here will generate a magnetic field, which will be connected to the secondary coil, which is in the phone. Then the phone will simply charge. However, that is in the modern technology. I doubt if they can have that set right here. Let's go to part C. Okay, good. So in part C, here we go. So in part C, they're saying, okay, let's go there. Okay, part C, they're saying, part C, number 1, help Dodoviko understand the meaning of the rating 7.5 ampere, 240 volts. I explained this, that when a device is connected to a 240 voltage supply, it will give out current of 7.5 amperes. Let's go there and look at that. Let's go there. Okay, let's go there. Let's go there. Okay, let's go there. We have this part here answered correctly, and we move on. Okay, so part Roman number 1, here we go. The meaning of the 7.5, 240 V. So the statement means that the fridge operates safely at a maximum current of 7.5 ampere when connected to a 240 voltage supply. Now you have to use the fridge, they can use the TV, they can use anything. But this is what it means. It means that this is the supply, this is the what it gives out. So the statement means that the fridge operates safely at a maximum of current. It means that once you exceed, if there are 7.5 ampere and use 10 amperes, the fridge can easily get spoiled, or it can even burn out. That's why that rating is really important and also good to be followed up. in simple terms. We have our part C Roman number 2 answered already. Let's go to part C Roman number 1. Let's go to part C Roman number 2. Let's go there. So part C Roman number 2, here we go. Alright, great. Okay. So part C Roman number 2, let's go there. Okay, great. Okay, now they are saying establish the cost of 1 unit of electricity if in a month Dodoviko pays a total of Uganda shillings this. Now they're giving us total expenditure on electricity which Dodoviko uses. They want to know how much does 1 unit cost. It is a very rare setting if you can look into this. The other setting you have been having has been more of calculate the total cost. Here they've given us total cost, they want a unit cost. How much does 1 unit of electricity cost? But remember in the question they told us that in the question, in the hint here they told us that, clarify here, each unit of electricity is equivalent to 1 kilowatt hour. So 1 kilowatt hour is equivalent to that. Then we shall base on that to get our answer. So they want to know how much does 1 unit cost if the total is that. It means that we must go about calculating. Calculating what anyway? Let's now look into this. You realize that here, what do we have? We have, okay, a fridge. Our fridge. A fridge is right here. Now let's say that let the unit cost be y. Let our unit cost be y. Now a unit cost will be how? Remember that from the word kilowatt hour. Kilowatt hour. Kilowatt is the power. So that to get the unit, to get the cost will be equal to, from that kilowatt, the power times time, this one the hour here, times time, the hours it takes, now times the total time. Total time. You know why I'm saying total time? Is because they want it after 30 days. We can know the time it can use in some number of days, then we convert to the 30 days. Say for example, our fridge operates for how many? Operates for 4 hours. You see that? Operates for 4 hours. So allow me to use this times. So yeah, it operates for 4 hours. That's the time. The total time is the time is that right here. Then we need the power. It's the only thing remaining. Let's come and see here. Then that, okay, all that time was now the unit cost. Times the unit costs also times y. To know how much it costs to use that in a month, times y. Of course, you know that calculation there. So it is power times time times power times total time. Total time is the 4 hours in 30 days, and even the, all right, the, okay. Also, we have to multiply with the unit cost which we have called the y. Now the power. How shall we get the power? A fridge operates for 4 hours. Noted, every day for 15 days. Here also now times 15 by the way. 4 hours times 15 to get the number of hours, but also times 30 to make it in per month. Okay. But now, do you have the details for the fridge? The fridge, do you have the details? Let's go there in the question. I see the details for the fridge, so that we need the power also. We need the power. We need the power. We need the power here. Okay. So in the hint, they are saying that the vehicle has a fridge rated by this. So you have the current and you have the V. So but from power, which is equal to IV, we shall multiply 7.5 times 240 to give us the power. If you can really see that. So let's come and say, now we calculate the unit cost for only a fridge. So it will be, power will be 7.5 times 240. Now all this times y, we shall get a unit cost for a fridge. We do the same for the bulb. We do this bulb. We do the same for the phone. Then later on we add. But of course they will all be having that value of y. After adding, we equate to this expenditure of Dodoviko. Then we get the value of y. Without wasting time, I think let's get there. Okay, to begin with, when you refer to the question, you're saying that let y equal to the unit cost. Then to begin with, we shall say the cost is equal to power in kilowatt times total time times unit cost. Total time I explained. Maybe it uses 4 hours for 15 days, which is okay. Then you must multiply by 30 to get the total time. You get me there? The unit cost, 1 unit cost is just y. If you can really look into that. Then the power in kilowatt can be calculated using the details we have in the question. Okay, to begin with, let's start with the fridge. So a fridge, you all know that the voltage given to us in the question was 240 volts and the current was 7.5 ampere. So but from power is equal to IV, we shall now calculate. This is our I times 240, we shall get 1800 watts, but we want it in kilowatts. So you divide by 1000, then we shall have 1.80 kilowatts. Then we substitute in our formula there. So time is equal to, now let's come and get the time. We have the power. Time will be 12 hours per day for 30 days. You know that. 12 hours per day for 30 days. Let's look at this. So this will be, alright, good. So we shall say the cost will be equal to the 1.8, which is this, times the 12 hours for 30 days. If you can really see that. Okay, 12 hours times 30 days, that's what I have right here. Then times the unit cost, which I have as y. Then you shall have that the cost of a fridge will be 180 y. That's the cost for a fridge in simple terms. Anyway, are these details we had originally? Let's go and check. Let's go and cross check. Okay, so please, I've made some clarification here. I'm really sorry, but I had to change this because what I had already was in this. So I've changed that. The fridge operates 12 hours every day for 30 days. I've changed that, and to have the same details like a bulb, I've changed it by the way because I didn't have time to have this changed all. In fact, I changed this one to suit our solutions we have the other side. So let's now get there. Okay, so here we are. We had that already in place. Now the time was for 12 hours per day for 30 days. I've changed it, please. For the refrigerator, I've changed it to what we had originally. I've changed that, please. You can rewind the video and see that. So now I have this. Now we can calculate. Remember, we see that our cost is equal to power in kilowatt times the total time times the unit cost. So our power in kilowatts is that we have the 12 hours for 30 days, you multiply them, total time, we have it there, times 30, then times the unit cost, which is y. So the cost for using a fridge in a month will be 108. We're multiplying by 30 because the total given to us was monthly, which is after 30 days. That's why you're also calculating like that. Next, we're done with the fridge. Let's go to the bulb. So with the bulb, the ratings given to us in the bulb, if you can go there, from power is equal to I squared R. We have that. Now about a bulb, allow me to take you here. About a bulb, allow me to take you here. About a bulb, here we are. In fact, our bulb is here. What do you have about a bulb? It has how many? 8 light bulbs, each rated at 4 ampere, 5 ohms, which is in simple terms our resistance. Now what are we going to do here? We're going to say, how shall we get the power for the bulb given these details here? Remember, this one here is I, this one here is Z, this one here is the resistance R. But remember, we know that power is equal, because we need power here, when power is equal to IV. But you all know that V is equal to I what? IR. So when you come and say that power is equal to, first of all, this I of ours, which you have there, times, now V is equal to IR, times again IR. You see that? Now you shall have that power is equal to, the I times I will give us I squared, times now the radius, the resistance, not radius. Now, but we have the current, which is 4 squared times 5, like that. Then the power shall get there will be 80 watts, which shall divide by 1000 to get it in kilowatts. Hope you have really mastered that. Then also you must go and see the time which they're using for this bulb. The time, as far as this bulb is concerned, is just here. The time is here for the bulb. They're saying each bulb, remember there were 8 bulbs, each bulb works for 12 hours each day for 30 days. Please, I'm again pardoning, I changed the details for the fridge. It was easier changing the details than changing the other side, the gate. Okay, I preferred that, and I'm very sorry. So Now each bulb works for 12 hours each day. That's the time. So that you can multiply the 12 times 30. But remember there were 8 bulbs, so you must cater for those 8 bulbs there. What the power you have calculated is only for one bulb. Okay. So with that, let's get there. Alright, good. Here we are. Great. So let's go there about the bulb. Now this is what I was explaining, that I squared R, you multiply this by that to get 80 watts, convert kilowatts, you'll have it like that. Now the time, we all know that. Okay, the time will be 12 hours per day for 30 days. So you multiply 12 times 30 to give it the time. But remember there were 80 bulbs, so shall say cost is equal to, there are 8 bulbs times the power for one bulb times the time for one bulb, total time for one bulb times the cost for one bulb. So here we shall have catered for the 8. They give you 12, you put here 12. Take note of that. So you have 230.4 in terms of Y, because this one here is unknown. This is the total cost for a bulb. In fact, I didn't even write it here. This one is total cost for the bulb. Next, let's go to the total cost for the phones. How many phones were we having right there? Remember the phones were, we had 3 phones. But of course, now just remember the phone, if you check in the details in the question, the voltage for the phone was 240 and the current was 4,500 milliamperes. Now we must convert this to ampere here by simply dividing by 1000. And you see, this ampere is equal to that, so you are dividing by 1000 to convert from milliampere to ampere. So we have the ampere, but power is equal to IV. We have the V here, the I, we got it. So IV 4.5 times that, we shall have that in watts, divided by 1000 to get it in kilowatts. Then bring our formula. Cost is equal to, there are 3 phones times the power for each phone, the time taken for, total time taken for one phone. So 3 times that times that times that shall have 145.8 Y. Now what does it mean? Here it means that we need to add the total cost for a bulb, total cost for a phone, and total cost for a fridge. Then we shall see the value of Y, which is simply the unity cost. Let's get there. So you realize that they're saying if in a month Dodoviko pays a total of 121,050, then what must you know? Shall see that now total monthly expenditure will be given by sum of each expenditure of each appliance. I'm meaning a fridge, I'm meaning a bulb, and I'm also meaning, okay, the phones. So you must get that done. So the total here is this. Now the total for each, we have it as this. This was for the fridge, this was for the bulb, this was for the phones. Of course, you shall be able to get the value of Y, collecting like terms. Now when you sum up these ones here, what will you get? When you sum up this plus that, you will get that. But it equals to this one, have it right there. So you're going to divide both sides by that. Okay, and after dividing, it will give us the value of Y. So the value of Y will be 250, meaning that each unit costs 250 shillings. That's determined by the way. Very little in simple terms. So with this, let's conclude and say, okay, shall say therefore each unit of electricity costs Uganda shillings 250. As simple as that. That gets our part C, Roman number 1 answered. Let's go to the last part and we call it off for now. So let's go to the last part. The last part, let's go there, which is part C, Roman number 2. Rather than just part C, but part D. Let's go to part D. So part D, here we go. They're saying identify the common house wiring components. Now wiring components, the ones you use, think about a wire, think about a fuse, even in your house, the components. Just look around in your house, what you're seeing there is what they want here, and explain to the villagers how each protects them. Now protects, you must not forget a fuse, you must not forget about the wires and their colors, you must not forget, in fact, that's what we're going to talk about right here. And let's go there without wasting time. Let's get there. Let's get there. So the saying, with the wires, they must have wires. Now red or browny color, which you call a live wire, it carries current. You have to explain to them. Of course, you know that in the normal wiring, we have red, we have blue or black, and we have green. So you must be knowing what these really mean. And please, if you look into the revision questions we have in physics, in a certain item I was explaining how these wires operate, or you can go in the playlist and check for UCE Physics Guide of last year 2024. I explained that. You can check that, especially in item 5 and 6. I explained how these wires operate. However, I shall have it more here again. Shall have more of it right here. So let's start explaining. So the wires can be red, blue, or green, or it can be red, black, or green, depending. So if you see blue, or if you see red or brown, red, of course, the red means danger. Live carries current to the appliance. It is very dangerous. You don't need to touch it. Blue or black, a neutral wire. It may not be harmful, but still you advise not to touch them. Of course, someone after watching this will go and touch anything. So long as it is green, it is blue, then it may end in tears in the long run. I advise you not to. So yellow or green, or what you call the earth wire, path for the stray current for safety. That's what it means. Then the switch, you know what it means. Connects or disconnects the circuit for control and safety. You know what that means. So about wires, talk about the colors. So you are having here wires, we are having a switch, we are having a fuse, and you are having a socket. I'll get you pictures of this so that you understand them. A fuse in a circuit breaker or plug of an extension cable melts when the current exceeds a rated value, protecting the appliances from overcurrent. So it protects those stuffs from burning down, by the way. That's what it simply does. And here we are. A socket is the power point fixed on the wall to supply electric current. Now, a socket is this. A socket is that. The wires, we have them here, wires, and this is a fuse. This one breaks the circuit. This one, the red, green, and black, we have talked of what they mean. Then a socket, we have talked of what they mean, and that gets part B of this question correctly and perfectly answered. Okay, it has been a lengthy video, but thank you for enduring. Let's move on.